Dear students, today we are going to deal with Newton's laws of motion and free body diagrams. The objective of this lesson is to solve problems on Newton's laws of motion using free body diagrams. What are free body diagrams? Free body diagrams are used to show the relative magnitude and direction of all forces acting upon an object in a given situation. In these free body diagrams, we represent all the external forces acting on the object and apply Newton's second law of motion. All the action-reaction pairs are ignored. If the system consists of more than one object, then the free body diagram are separately drawn and solved. If you take the case of a string, all along the length of the string, the same tension exists at all the points. Each small part of the string has the same tension, trying to pull it apart in opposite directions. Let us now look at a few examples to make the concept of free body diagrams clear. Example 1. We have a block of mass m resting on a horizontal surface. So this is the horizontal surface and the block of mass m is placed on it. We are assuming that there is no motion. That is, all the forces are balanced. The weight of the block mg is acting vertically downwards and the normal reaction force is acting vertically upwards. The gravitational force always acts perpendicular to the earth's surface and the normal reaction force always acts perpendicular to the surface on which you place the object. Now, a force F is applied onto the block. Since the force is applied in the rightward direction, you have friction in the leftward direction. Friction is always parallel to the surface and it is opposite to the motion of the object. mg represents the gravitational force and n represents the normal reaction force. Since we are considering the equilibrium condition, we have n equals mg and F applied equals frictional force. So we have seen the free body diagram of the block resting on a horizontal surface and the equations that we can derive under the specific conditions of equilibrium. Let us take a more detailed example where we can draw the detailed diagram of free body diagrams. Example 2. Let us look at the question. A mass m is suspended by a rope of length L from the ceiling. A force F Newton is applied horizontally at the midpoint of the rope. Find the angle the rope makes with the vertical in equilibrium. So according to the question, the length of the rope is L and a force which is horizontal is pulling it to the right so that the rope makes an angle theta with the vertical. Now we have the mass of the block as m. How do we draw the free body diagram and calculate the angle? Let us try to look at the diagram in an elaborate way. The block M has its weight acting vertically downwards, mg. and there is a tension acting along the string. Now the force F is horizontal, so it doesn't have any other component. Let us take this tension as T2, and there is, for this part, there is another tension, say T1. Now if you look at the forces, T2 is along the y-axis and F is along the x-axis. But T1 is neither along the x-axis nor along the y-axis. So T1 can be resolved or divided into two components, rectangular components. That is, one along the y-axis and another along the x-axis. The y-axis component is the cosine component, that is, it is T1 cos theta. According to geometry, you know that if we have a right angle triangle, the opposite side is always sine component and the adjacent side is always cos component. So if this is F, this will be F sine theta and this side will be F cos theta. So this part will be T1 sine theta. So you can see that when we resolve the tension as T1 cos theta along the y-axis and T1 sine theta along the x-axis, and assuming this is an equilibrium condition, the diagram gives us, the diagram looks like this. It gives us scope for writing the equations. So let us have a clear look at the diagram. The free body diagram for the block M is tension T2 acting upwards and mg acting vertically downwards. And the other diagram is F acting rightward, T1 sin theta acting opposite to it, T1 cos theta acting opposite to T2, and T1 is at an angle theta with the vertical. So under equilibrium conditions, what can we say? For the block M, we can say T2 equals mg. It is balanced. The other equation that we can assume is F equals T1 sin theta and T1 cos theta equals T2, which is equal to mg. Now, if you write the equations in order, T1 sin theta is equal to F and T1 cos theta is equal to T2. Take the first T1 sin theta equals F as first equation and T1 cos theta equals T2 as the second equation. If you divide 1 by 2, you get tan theta equals F upon T2, or theta equals tan inverse F upon T2. So, by drawing the free body diagram, we can analyze the situation and use the equations from the free body diagram to find the angle. I hope this example is clear. If this example is clear, let us move on to another example. Example 3. Okay, right. A ball of mass 5 kg and a block of mass 12 kg are attached by a lightweight cord that passes over a frictionless pulley of negligible mass. The block lies on a frictionless incline of angle 30 degree. Find the acceleration of the system and the tension in the cord. So you can see the diagram here. This is an inclined plane and the it is with respect to the horizontal, the plane makes an angle 30 degree. You have a pulley here and there is a block of mass 12 kg and this ball of mass 5 kg. The whole system is moving with an acceleration A. Now, to find the acceleration and tension, you need to draw the free body diagram for this particular system. Now, as per the earlier examples, we know that the weight of this will act downwards. That is 5 into 9.8 or 10. In this case, we can take it as 10. So 5 into 10, which is equal to 50 Newton, is the weight that is acting downwards. Now there is a tension acting along the string. Now this 12 kg is on the plane which is at an inclination of 30 degree with the horizontal. So this weight of this will act 12 into 10, that is 120 Newton, is acting perpendicular to AB. So let us take the surface as AB and this point as C. So the weight of the block will be perpendicular to the surface of earth, which is AB. Now the reaction is, the normal is perpendicular to BC. This is the normal force. Now under this situation, there is a component of the weight that is acting along the surface downward and another component along that is opposite to the normal. Now this is same as the previous case. This angle is 30 degree. So here this angle is also 30 degree. So this is mg. mg is 120. So it is 120 sine 30 in this direction and 120 cos 30 in this direction. So these are the components. Now there is the tension along the string. Since the block or the whole system is accelerating in this direction, you can see the direction here, the downward force is greater than the upward force. Here also, since it is moving up with an acceleration, the upward force is greater than downward force. You should always remember that F net equals MA. It is in the direction of greater force. It is always in the direction of greater force. Right? Let us look a clear picture of this to solve it for the equations, for drawing the free body diagram and the equations. So, look at the diagram here. Here, the weight is acting downwards, the tension is acting upwards. This is 50 Newton. Right. If we draw the free body diagram separately for the ball and the block, you can see that 50 Newton is drawn with a short arrow and tension is drawn with a long arrow, showing that tension is greater than 50 Newton. Tension is greater than 50 Newton because the acceleration is upward. Now if you look at the other block of 12 kg, you can see that 120 cos 30 is acting opposite to N and 120 sin 30 is acting opposite to T, and the acceleration is in this direction. So the free body diagram gives as the equations. For the ball, we can say T minus 50 equals 5a. And for this 12 kg block, 120 sin 30 minus t equals 12a. Now, if you have any confusion regarding the equations, you should always think that acceleration is in the direction of greater force. So, greater force minus smaller force is net force. Here, tension minus weight equals MA, 5A. This is 5, so 5A. 120 sin 30 minus t equals MA. This is 12, so it is 12A. Now if you take the equation, t minus 50 equals 5A as 1 and 120 sin 30 minus t equals 12A as 2. If you add the first and second equations, the tension gets cancelled on adding. The tension gets cancelled. Now, sin 30 equals half. So, sin 30 equals half. So, 120 sin 30 is 120 into half, which is 60. Alright. So, you get the equation as minus 50 plus 120 into half equals 5a plus 12a, and you get minus 50 plus 60 equals 17a. Now, on solving this, you get the acceleration as 10 equals 17a and a equals 10 by 17, which is 0.59 meter per second square. If you substitute the value of a in t minus 50 equals 5a, you get the tension as 52.95 Newton. I hope this example made the concept of equilibrium, free body diagram and F net is equal to MA clear. Remember students, we do not represent any action-reaction pair in the free body diagram. We only go for external force and apply Newton's second law of motion. Thank you.